record. Okay.
Wait, this question came from TST of something.
Where's TST?
Okay.
Team selection test.
Let
A,
B, C.
Did I slip?
Was it
C.
Germany? Yeah. Oh yeah, Germany.
Let A, B, C be a triangle with orthocenter H. Actually, this is irrelevant. H and circumcenter O. I guess I'll just estimate where the circumcenter is.
Yes, I saw the no conjugate.
Yeah. Okay. Let P be a point in the plane such that AB is perpendicular to BC. So it's like some point on this line. I guess I'll just draw it here. It could just be wherever here. Okay. Let Q and R be the reflections of P in the lines CA and AB. So it's like I reflect this up here, I guess. And I reflect this up here.
The left one is R.
Wait, let me check.
P could be inside.
R is, yeah, P could be just wherever, literally wherever on this line. Reflections CA and AB. It's a Q, R. And then let Y be the orthogonal projection of R onto CA and let Z be the orthogonal. So it's basically like you reflect it in one of these two sides,
Yeah.
and then you project it onto the other side.
Like the foot perpendicular. Okay.
Wait, do they make that the same?
So it's like you project these two on here. And now my diagram does not make this look true.
Are they called X? Is they called different letters?
They're called Y and Z. So Y is
R and Z is Q.
okay. Prove that. Assume that H is not O and Y is not Z. Prove that Y is Z. This doesn't look true in the diagram. I'll draw the two lines. Y Z is perpendicular to HO. That doesn't look right, but whatever. I can't draw. Anyways, you have to somehow prove this. So Lucas made a good observation, which is that you can use MMP for this problem. So MMP is the method of moving points. So a lot of the time in problems, you're given a point that can vary on a line. So P, right? P varies on this line over here, this vertical line. That's like the altitude of A. So that's pretty cool. It can vary on a line. And a lot of the time, you have to prove a condition that depends on some points, Y and Z. So Y and Z is what it depends on H. Right. And these points are defined in terms of P and a bunch of other stuff that doesn't move, such that they are projective transformations of P, or something like that. And I guess I don't like projective transformation. Do you guys know what that is?
That's where the cross ratio is preserved.
Okay. So technically the definition of a projective transformation of the plane is an invertible transformation of the plane that preserves lines, so preserves collinearity. So like takes points to points and then lines to lines.
What?
But honestly, that's pretty AIDS. So
that's true.
So I'm just gonna say like a projective transformation of a line is
take points to lines.
I'm just gonna say that a projective transformation takes a line. Well, at least this is an example of one, and then projects it onto another line. So you basically like take a point and then you like draw lines, and basically like the corresponding. If you have points on this line, then the corresponding points after the transformation would be the points on this line where I projected them. If I take this point here, so that would be an example of a projective transformation.
A point in line.
So the transformation itself takes the points on the first line to the points on the second line, yeah?
Yeah.
And then the way it's defined is using just some fixed point That's not on either line, yeah?
But like, how do you know when to stop the raise?
You stop when it hits the line that you want to get it on.
Oh, okay. So you need 2 lines and a point.
Okay, so I guess that's an
The 2 lines are the
example.
ones that you want to transform. So the automatic type moves.
Okay, so that's an example of one.
Then you got to pick the skill.
I guess another thing to note is that in projective geometry, you have things called points at infinity, which is like not all. Okay, in normal geometry, not all lines meet at a point. Parallel lines don't meet at a point, and so in projective geometry, we want to make that true again, like so that every single pair of lines meets at a point.
Yeah,
So pair of parallel lines, we kind of define a point at infinity that's like infinitely far away in this direction, or like this direction, they're equivalent. And so pretty much every direction mod 180, we define a point at infinity, I think.
Yeah. It's kind of like, if you look at the roads in the distance, it actually looks like they meet.
It's like quite goofy.
Yeah, and the motivation for it is that you're kind of like completing it.
Yeah, so it makes everything well defined when you're just talking about like incidents. So I guess a cool thing you can do now is like this point can be like a point at infinity. So this point that we're projecting from can now be a point at infinity. So now we still have 2 lines, but this time the point is at infinity. So all we're doing is drawing parallel lines like this. And now these are the new points, I guess. This is pretty funny. Actually, I don't think I've explained everything we need for the problem, but I'm just gonna need you to trust me, bro. Alright, anyways, okay, so we also have this thing called the cross ratio. So the thing about projective transformations of lines is that the cross ratio of that is preserved. So under projective transformation lines, we have something called a cross ratio, which is like if you have 4 collinear points. Actually, I forgot the definition of a cross ratio. Let's go. It's like the ratio of the divisions.
Yes.
So it's like it's a cross ratio of A, B, AC. Okay, that's actually a better way of doing it because B is inside and D is outside. So this is a definition. ACB is like, hold on. It's something along the lines of like A, B on BC divided by AD on these or something like that. I don't know. I'm hand waving a lot right now. Also, I don't know. Wait, how does this work?
I think it's the ratio which B divides AC internally over like the ratio which D divides AC externally. So like it should end up negative, yeah.
Yes. So I'm actually, the problem is like I don't know what the directed length directions are.
AB on BC over AD on BC.
Yeah, I'll just define it whatever.
As long as you had it right.
B on
BC.
Yeah, so because DC is negative, so the whole thing's negative.
Okay, so we just randomly define this cross ratio without any motivation whatsoever. Now, here's the claim. The claim is that projective transformations preserve this. So if you perform a projective transformation of A, B, C, D, it preserves this ratio.
Did you get that, Andy?
Yes, I wrote it down.
Okay, and I'm not going to prove that because I don't know. Like, actually, I did try it once.
You get to find it like that for now.
But yeah, okay. Anyways, just trust me, bro. It preserves. Trust me, bro. Okay, so the cool thing about this is that given a cross ratio and given 3 points, say we don't know what D is yet. Say we're just given A, B, C and a number that is the cross ratio. Then we can find D.
Like D is uniquely defined.
Yeah. So it's like if there's only one D such that A, B, C, the ACBD is equal to something that I say.
Yeah, so like basically if you know where A goes and B goes and C goes, and then you know where D goes.
Okay.
Does that make sense?
Yeah. It looks like you can just do algebra.
So you just do some algebra to figure out where D is.
Okay.
The entire transformation is determined by 3 points.
Yeah.
We get y.
Okay, so now look at this diagram. So what is R a projective transformation of P? Yes.
Because it's a reflection.
So R is just a reflection of P over this line.
Yeah.
And I hope you trust me that this is a projective transformation because
I think to make people understand that it's projective transformation, like it's easier if like people know what's being transformed. So like
All right, so let's reflect the line AP over this thing, right? Okay. I guess let's reflect the line AP over AB to make this thing.
The 2 lines in green.
So, like so. It's like, gosh. Okay. It's like that. I'm reflecting it across AB. And then I kind of take the point at infinity in like this direction that's perpendicular to AB. And then I'm like projecting P from that point onto this new line that I reflect. I guess that's a way you can define a...
Wait, again.
So basically what I did was I took AP,
Okay.
I reflected it across AB to make this new line. And then to define R, I define it as like the projection of P from the point at infinity in this direction, which is like perpendicular to this line AB, onto this new line. I guess it's a mouthful, but like I don't know if you get it.
Okay.
Yeah, I mean there's kind of 2 ways of looking at it here. So like as long as it preserves the cross ratio, that's sort of like the definition of a projective transformation, right? So even if you just think of the reflection, it's kind of clear the cross ratio should be the same, right?
Yeah.
But
yeah, because the lengths all stay the same, so therefore it's a projective.
But there's a particular type of transformation that we tend to express things in terms of to really make sure things are preserved cross ratio. So like when you have 2 lines at that point and you draw the rays from that point, that's called a...
Yeah, so if you remember this thing over here, this is basically doing that.
That's called a perspectivity.
Okay.
Right, where like I put parallel lines, and in this case, like the parallel line is like this thing. And it varies as P moves. So, okay, so that's a projective transformation. So R is a projective transformation of P, and Q is also a projective transformation of P by symmetry. So now, Y and Z. Okay, Y is clearly a projective transformation of R, because R is just being projected, literally projected, it's in the word, projected onto AC. And Z is Q projected onto AB. So that's a projective transformation.
Okay, so like again, like it's the green line that R is on, right? The points on that line is being transformed onto points on
It's
AC,
being done this thing again to
sense?
make this.
Yeah, but like it looks really odd.
Yeah, it does
And I'm not sure
tend to look weird. Yeah, my point is that Y and Z are projective transformations of these 2. Okay, cool thing about projective transformations, you can compose them to make new projective transformations. So if you do one projective transformation and you do another one, it's still a projective transformation. And I guess one way of seeing that is like, well, first, I guess the different definitions. Like, for example, if it preserves the cross ratio. Like, if it preserves the cross ratio twice, it just preserves it once in a total. And then also, if you're defining it as like preserving lines, preserving collinearity, well, obviously that's also true if you do it twice, I guess. Okay, so my point is that because of that, Y and Z are both projective transformations of P. Okay, so the cool thing about this is the method of moving points. Because once you have these 2 points that depend on P being projective transformations of P, you can kind of pick 3 nice places for P to be. And then prove that the property is true for Y and Z in those 3 cases. So for example, I could pick P is the orthocenter, right? So I could pick P as H. And then obviously P equals H is like a very specific case. So it should, and I have a lot more information, so it should be easy for me to prove it. It's easier for me to prove it, right? Or bash, which is what I did.
So you did.
Yeah. And so you can prove that YZ is perpendicular to HO in that case. Then you pick P as something else, like I don't know. I
What if
picked.
it's like on BC?
Oh yeah, you could do that. Yep.
Is that good?
Yeah, you could do that. And then you prove it again. And then you pick another point. And I guess the naive way is just to like pick this point, which is like the reflection of H across BC. It's like over here. So if you prove it's true for 3 points,
You can find the fourth point.
then yes, you can pick any fourth point whatsoever.
Wait, why do you have to do it for 3?
Because, as I stated before, if you have 3 points and you're given a cross ratio,
But what's the cost ratio?
So 3
It
points
doesn't matter.
determine.
it doesn't really matter.
3 points
It's some
determine a
cost ratio
projective
that will be the
transformation.
same no matter what.
Just know that it's some constant. Just know that it's something. Then we can pinpoint the fourth one.
But what's the fourth
It's
one?
unique. It exists and it's unique.
Yeah, so it's unique. And further, okay, so it's unique, right? So now that you've proved it for three possible places for P, you can pick any fourth one on this line. So pretty much everything, and then you can find, and then you know that there's like by this cross ratio, there's like a unique point for Y and a unique point for Z. So you know exactly where it is. And furthermore, because this perpendicular condition is kind of like it's kind of projective. I don't know how to explain this part. You know that it must also be perpendicular for any fourth point P. So pretty much it's true for any P. It's very hard. This is so hard to explain. It's like
Yeah, you need projective as a precursor to
this
it.
is so difficult to explain because it's like
Okay, so basically, like if you have 4 points on a line, right? Yeah. And you want to take them to another 4 points on another line via some projective transform, right?
Yeah.
So first you figure out where A goes, right? Then you figure out where B goes. Then you figure out where C goes,
But there's
right?
only 2 points to find the line.
But once you figure out where A, B, and C go, okay,
You know what D goes.
then where D goes is determined. No, it's not.
But like, what is D?
so D is your P, which can be any.
other point. D is any other point.
It's like pretty much any other point on this line, which is what we want to prove. We want to prove that it's true for any point P on this line. So P varies on this line.
Isn't like the ABC, one is P, one is Q, one is R, right?
Yeah, so P is our moving point.
Wait, no. For your like projection thing, you need 3 points, right?
Uh,
Oh wait, your 3 points are just like the 3 positions of P. Alright.
okay, I should have explained this like 3 points define a projective transformation of a line or whatever. Like, it's probably better.
I think another way to explain it is
Yeah.
like. Okay, so do you understand the three? It's actually called the fundamental theorem of projective geometry. So if I give you some context there, that'll maybe. So the point is, so if you have a projective transformation, right? Yeah. Like you might not like you find out where A goes, you find out where B goes, right? You find out where C goes, right? And the point is, once you know where those 3 go, okay, if another transformation sends ABC to the same 3 points, then it's the same transformation. You understand?
Yeah. So pretty much if you know where 3 points go on a projective transformation of a line, you know what the transformation is. It's a unique transformation.
So you can define the transformation here in like 2 ways, right? So here you can do like, so what Alex did to get Y and Z, right? Or you could define Z from Y to be like the perpendicular to the P thing, right? Yeah, that's projected, right? So you can define Y as the point on BA such that Y X is perpendicular to PO.
YZ. Yeah.
So if
the
that's
HO.
projected,
So YZ is perpendicular to HO, but that is projective from Y to Z. Yes.
So if that's a projective transformation, right? And because it agrees on 3 points with the other one you defined, it has to be the same transformation, right?
Okay.
And so if it's the same transformation, then all the points have to be perpendicular.
Yes.
Because that definition makes them all perpendicular, right?
It's like you're trying to find out information about this transformation, and so you just need 3 points. And then
who understands this point?
So
So basically, summarize.
Please help me.
So 3 points determine a projective transformation. Yeah.
yeah, I guess I get what's happening, but I don't know why it's happening.
What?
Yeah, I guess you don't really need to know why.
Basically, what the
Well, at least
for practical
specifics.
purposes, okay, what the method of moving points does is it reduces sort of like the general point P to 3 special cases of P. Okay. All right. How does it do that? The fundamental theorem of projective geometry says that 3 points determine a projective transformation, right?
Okay.
So if we can define like y and z in 2 different ways, right?
Yeah.
So in one of the ways we define it to be like, left, this projective transformation on the left, projective transformation on the right, and then they meet. And then the other way of defining it, just define it to be like the projective transformation to get to the x on the left, and then literally take the perpendicular condition as the way to define y, right? And those 2 transformations, if they agree at 3 points, are the same transformation, okay? So in other words, if you prove it's perpendicular for 3 points in the first definition, then it's perpendicular for all the points on the line, on the green line, yeah?
Yeah. So all points on the green line will satisfy this condition after this.
Okay, another side note was, this was what was done in the AMO, and it was not a projective transformation, but the markers still gave them full marks.
Yeah.
I didn't realize.
Wait, what? Make up mark.
So Chris in the AMO fake solved question 4 because he claimed it was a projective transformation and then did MMP on it. It wasn't, but I think Andy Tran was marking.
Yo, Andy Tran.
I don't know.
So, like,
I don't know who it was, but
if
it
you
was
have-
probably.
So maybe he should get like 1 mark for each of the special cases.
Like, he still gets gold though. Like,
Yeah,
nothing really matters.
it doesn't matter, but like
Well,
it's
what-
still
what
kind of
difference happens
it's
for more
negative.
than 1 question?
It's
Yeah,
funny. It's more funny. Like, it's not
it's
something-
really
It's like
it's like is the
other
AMT
marking
qualified to do the job?
And then Geo question 6 or something. It's like also an MMP fixed up. It's like 2 questions.
Whoa.
Wow.
Okay.
Whoa.
All right. Anyways,
Do people understand what's going on?
I'm a
So he's claiming that to prove this question, it suffices to prove it
3
P
points.
equals the orthocenter. P equals what else did you have?
so what I did was
The reflection of H on the circumcircle.
P is the orthos. Oh shit! Because for the sake of complex bashing,
Ah.
I proved it for P is the orthocenter. P is the reflection of the orthocenter across BC, and P is the reflection of A across BC.
Wait, did you do this question in like an actual test?
Hmm?
Did you do the question in an actual test?
No,
Oh.
I am not good at tests. Okay, so those are the 3 special points of P. It's H, this point, and this point. So that's what I did originally. And so I started with the orthocenter because if you reflect it, it's nice and complex bash.
What was the last point?
The reflection of A across species.
Oh.
Because it would be reflection formula nice. So, alright. First I did H because then R and Q would be points on the unit circle and that would be cool. And that was pretty chill. Then I did this point. It was this reflection point. It was slightly less chill. It was still chill for the most part. And then I did this point. And it was kind of cancer, I'm not gonna lie. It wasn't that bad once you see it, because like once you see the algebra trick, but like it was pretty bad. Well, not that bad. It was like bad for me because I don't complex bash much. Okay. But then I realized I was being a dumbass. So The thing about this problem is Lucas observed it was MMP. Like, it was projective.
Yeah.
But it's something stronger than projective. I don't know if the word for it is affine or something, but like affine. I don't know, something like that. But my point is, it's not just projective.
Okay.
Like, for example, P reflect across AB to R. That's affine.
What is affine?
So affine.
It's just like kind of like dilation along the plane.
How do I explain?
You stretch, you stretch and squish on the plane.
I find men like preserves lines.
Yeah, it preserves lines and I think parallel.
Those angles.
It's like preserves lines and parallel.
Does it preserve angles?
No, I don't think it preserves angles.
It
It's like any matrix transformation, like
doesn't
with like
angles.
or like this or something.
Yeah.
Like, so it preserves parallel and lines. I think that's what I think. I think it preserves lines and it preserves them being parallel.
The fine transformation is just like squishy and stretchy.
But yeah, it's squishy and stretchy. Okay, so but yeah, anyways, P reflect across AV to R. So reflecting is affine, right? Check that for yourself. And then R project onto this thing, and Q project onto this thing, to Y and Z. That's affine. That's affine.
What's the definition of affine?
It's like you don't define it and then start saying everything.
Alright, anyways. I think the way I would define it in this context, because we don't need most of the definition, is like basically if you have a line, it's like being able to translate it, rotate it, and dilate it. Well, at least, yeah, as far as a line goes, being affine just means you can translate the line.
What can you translate like any line?
The affine is a transformation of the entire plane, right?
Yeah, but for the purposes of only considering a single line, the affine transformation is just being able to translate it. It's like move each one of these points.
When is it not affine?
It's when it's not this. Okay, it's not when it's not what I just said. It's like being an affine transformation of a line in a plane is basically like being able to translate it, being able to rotate it. So like rotate it and being able to scale it up and down. I guess like.
But isn't that like everything you can do with a line?
No.
What?
You can do whatever. It's just a function. Like you can do whatever you want with it. You can mangle the line however you want. But like this is a very specific function on the line.
What?
It's like you can.
You're saying you can realize it with a rotation, translation.
It's like if two lines are affine, then they can like be like squished and like translated into the same line.
Yeah, I get it's not exactly transforming the line. It's transforming all of the points on that line. I think that's a better way of thinking about it.
Wait, are you defining an affine transformation like between collinear points to collinear points?
Yes.
Or...
So I'm just saying, like, in an affine transformation, what happens to the points on a line?
You're kind of doing like a 1D affine transformation.
Yeah. So I guess, yeah.
So you're saying like, so you have one line and you have another line, right? And then the points are related by an affine transformation. Then you can kind of, there's like, for example, there could be a rotation of the whole plane, which takes that line to that line, and those points go exactly to where those points go under the affine transformation.
I guess it's pretty hard. It's pretty hard to do this because, like, I kind of just randomly thought of this. But yeah, anyways.
I guess the natural question is, what is the difference between affine and projective?
So the thing about affine is, like, I guess it preserves just ratios on a line.
It preserves ratios, just full stop.
It's just ratios, not just cross ratio, just ratios.
It doesn't have to go to cross ratios.
It's just ratios.
It preserves ratios and obviously preserves cross ratios.
Yeah, it just preserves ratios. And the good thing about preserving ratios is that it's no longer 3 points to find a transformation, it's 2 points to find a transformation.
Wait, couldn't
Isn't two points to find a line?
It's complicated.
Dang it. Yes, 2 points to find a line, but I'm not talking about 2 points, I'm talking about what happens to the 2 points on the line.
He got you there.
But-
we already know the points on the line go to the
Yeah,
points
we-
on the line.
Yeah, he got you good, Alex.
Damn, I got
2
God.
points,
I
2
got
points
God.
to find a line, dude. He
I got
you
God.
good.
But yeah, 2 points to find.
2 points once defined a line, but now they define an affine transform.
Oh my lord, this is confusing as hell.
I have a
Fine,
proposal.
Huh?
Why? Wait. Okay. Like this is not related, but
Fine.
by homosity, right?
Yes.
Like consider like fixing like fix P
Yep.
and then move BC.
Fix P and move BC.
But like the thing
How's
is,
that work?
And then wouldn't like YZ stay in place? So for any
yeah.
P, then YZ, all the YZ are parallel.
Mm,
So don't you only need to do 1 point of P?
yes.
Oh,
One point.
genius gameplay.
Pro
hell?
gaming.
We're improving.
Pro
we're
gaming.
improving.
No. I'll get to that. I'll get to that. But anyways, this is the journey to the final solution. Alright, this is the journey to the final solution. Yeah. But basically, I discovered something similar to what he discovered eventually. But I'm not there yet. But yeah.
Dude, it's like it's not moving points. You just deleted all the points.
Yeah, I just removed everything.
It's
Like everything got
removing
deleted.
Points.
Alright. So,
Instead of removing
but yeah, anyways. So now because I've realized that like y is an affine transformation of p and z is an affine transformation of p, this annoying point down here that was really aids to complex special, let's just not use it.
It's just
I don't like it.
It's just H.
Okay.
Wow. You only need H? Damn. And
So-
that's simple. That's pretty simple.
So you can do h and this, right? For now. But I still said this was kind of annoying. So let's delete one more point. Okay, so there's been an assumption that I've been making the whole time when I was picking this point. Which was this, picking p's. Like picking p's. Which was this thing. Assume that h is not O and y is not z.
Well, I think whatchamacallit.
So h is not O and y is not z. So obviously in the definition of the question, h cannot be O and y cannot be z. Because otherwise yz is not defined the direction and h is not defined the direction. Like you can't really say they're perpendicular.
Mm-hmm.
But for the purposes of my proof, I don't even need this condition. H can... Okay, h still can't equal O. But in effect, y can equal z.
Could it?
But how does Y even?
How like if P equals A?
Yeah.
Oh,
So actually, I can just get rid of this point as well.
The problem is if you move your BC, right? It's
Wow.
But yeah, I'm gonna get rid of this reflection point as well because it wasn't that nice either. And just pick H and A. And can you notice what happens?
It's degenerate.
Yeah, it's degenerate when I pick A.
Okay, so like,
Okay, so what happens to when P equals A? A gets reflected across AB to R, but then it just stays as A. And A gets projected onto AC, so it just stays as A as well.
Okay.
So pretty much Y equals Z equals A.
Okay.
Okay, so they're all the same point. That's pretty funny. Can you see that if I prove this property for A and H, then I can prove it for everything?
Wait, what are you proving? What are you proving for A?
What?
What property
you
are
don't
you
even need
proving?
to prove it for A.
So for A, I'm proving that Y equals Z equals A, which is pretty obvious.
Oh, is that what the property amounts to?
So Y equals Z equals A. The thing is,
Like, does Y equals Z equals A show the property?
yes,
Oh.
because Actually, I'm not. I'm not exactly sure how to explain this. But yeah,
You don't need that just from Victor's observation.
but yeah, Victor. I think Victor's observation is kind of
So
similar
maybe the
to my
property, the
observation.
property that
It's
you're
like,
showing is that it agrees with that projected
yes,
that transformation.
it's like this transformation. If you were just to apply it like this perpendicular to this prop condition,
Yeah.
then if you make it degenerate, it's true.
Huh.
Right? Because if I move y here
Okay.
and then I draw a line, it still intersects there.
Okay.
So it does agree with that affine transformation. So now A is trivial and I only need to prove for H. So that's like the massive simplification of the problem. And now we bash.
No,
And that's it.
You could synth it. It's
Yeah, you could synth it, but like I wasn't
So you bash
bothered.
it for H and A.
I don't bash it for A, it's just obvious.
Oh, A is just true.
For H I could bash. Lucas said synth is possible.
It's possible because pure reflections are on the circle, which is 9.
Yeah, but like I bashed it because at the time I was bashing all three. So I guess H.
Wait, how does this relate to Victor's comment with the?
Well, it's similar because it basically amounts to the same thing, which is that you only need to do 1 point.
Oh.
Because A is obvious, and Victor's kind of like similar because like you're basically fixing A as well.
Oh.
Is like I don't know if that makes sense.
So you change BC.
Yeah, you
Instead of
change
changing
BC instead of changing P. And so A kind of does whatever. And then YZ is just a dilation.
I guess
It's kind of like that.
to check it, you have to kind of spend the time to check that write out what the transformations are, and then like figure out what the properties they should have are. You can't just assume it's objective because someone said it was.
Yeah, basically the point is that A just agrees by default, so we just have to do H. And now we bash. Okay. So
Can Lucas bash this? If you were pushed against the wall, what's the
it's
bash?
not that bad, I think.
Bash will be bashed.
But is it a bash plus H?
Bash will be bashed.
Yeah, we're bashing P equals H.
Wait, what did you say, Vito?
Well, I was debating whether it would be easy to bash on H or like the reflection of H.
Oh, reflection of H.
I don't know.
Reflection of H, you get.
Yeah, it is on the circle, but the problem is once you reflect it, it's across A, B, and AC. It's really weird. Whereas with H, when you reflect it across A, B, and AC, it is on the circle. So it's like you're on the circle for an extra.
That's true.
Yeah, and then when you get it on here, obviously it's gonna get a little bit messy, but it's fine. Like, it's manageable. Okay, so should Lucas do this or?
Give complex bash tokens out.
Okay. So we do like A and then B and C on the unit circle. H equals A plus B plus C. I think the thing is, these points are well known to be something nice, but like I need to do it.
So in like an ideal world, but in principle, if you prove it's true for a special case and method of moving points was possible, you should get marks. In an ideal world.
Yeah. In an ideal world, if you just prove it for one case, then you're done. So you should get most. They're like you're just like, oh, I just proved it for a random case. I'm getting like 2, and then suddenly you get 5.
That was the only case you did.
But yeah, okay. H equals A plus B plus C. Now we reflect H across A B. The reflection formula is R equals A plus B minus A B H bar equals A plus B minus A B
Well, what thing
A
is
bar.
the center, right?
Plus
Yeah.
B bar
B is
plus C bar equals A plus B
is
minus
like when someone else is complex.
B minus A. So this all cancels.
What?
And it makes sense because it's on the unit circle,
But
by the way.
A bar
So it
is
should
one
just be a
vector, right?
product of
Yeah,
like
yeah.
A, B, C in some way.
What's ABC bar?
A bar, B bar, C.
Oh, you just haven't written it in.
So it's just minus
It's
ABC bar, right?
minus ABH bar because of reflection.
In the
And then I just subbed it in.
Yeah.
And
you
then
haven't written the ABC bar yet, is that what you're saying?
yeah, I haven't
Oh,
written it. Okay, so it's just ABC bar.
Minus
Yeah, well, minus ABC bar. Yeah.
That's R.
Okay.
That's R, right?
Okay. Anyways, let me just.
Oh, that's what you wrote. You wrote R.
Yes.
Yeah, it's R because I reflected.
Yeah, and it's clearly on the unit circle.
And likewise, Q equals minus A B bar C because symmetry.
Huh?
Hmm.
That's pretty nice so far.
Okay.
And then you just need X and Y.
So now I need Y and Z.
Oh, wait.
Yeah, they're Y and Z, but I wrote them weird because I'm bad at writing. There's no X. This is Y.
That was never.
There was never an X. It was Y and Z.
Oh, interesting. X got skipped.
There's no X. Okay, so now we need to find Y and Z, which is like the projection. And you can think of the projection as kind of like reflecting R across and then averaging the two. It's like taking their midpoint. Right? So then you get something like, if you were to do that, then you get like R plus R prime on 2, where R prime is the reflective version. And then you get like Q plus Q prime on 2. And then at the end, what we want to do is minus them to get the line vector. And then prove it's perpendicular to HO. But notice there's a factor of a half. And the direction is preserved on the multiplication by a scalar, so we can just delete this. So now it's just R plus R prime minus Q plus Q prime. Yeah, but the way I did it was actually kind of weird. But I feel like it's not that bad. Okay, firstly, let's try and find R prime, I guess. R prime equals A plus C minus AC R bar equals, I can't do algebra. Plus AC ABC bar.
Oh, yeah, you just like it.
A squared B plus, wait, yeah, that's it. A squared B. Is this right?
Yes.
Yeah, this is right. Okay, and then Q prime is like just that, but opposite. Okay.
Lucas, are you avoiding the complex back? Are you curled up in a fetal position? Avoiding the complex back?
He's in the fetal position. This is right? Surely I'm not making a mistake. Okay.
Q prime should be the same as R prime.
Q?
Like,
Yeah, just because they're symmetrical. Okay, so now we need to find R plus R prime.
Could you do R prime minus Q prime?
You could.
R minus Q.
Yeah, you could, but I don't know. I'm confused.
Okay.
R plus R prime equals A plus C. Wait. Hold up. I'll just do minus A B C bar first, and then plus A plus C plus A squared B. And then Q plus Q prime is the same thing. Minus A B bar C plus a plus b plus a squared c. So I think that's right. Yeah. Okay. So now we subtract them.
Oh, that's a factor.
Yeah, there's a factor. Okay, so a's cancel out. Now I do now I subtract them, so I get a b bar c. This equals a b bar c minus a b c bar plus c minus b plus a squared b minus a squared c. Okay. There's a factor of a in this. That's pretty cool. So I guess I'll just get it out.
What happened?
Wait, hold on.
Wait, it's factor of A.
Wait, no, there is not. Wait, I'm dumb. I don't even know my own complex batch because I said I forgot it. Anyways, what I wanted to do now is factor out a plus b plus c.
Oh.
Because we want to prove that once we factor it, the other factor is imaginary, so that it's perpendicular. That's what I did, but
I guess the obvious factor here is b minus c.
yeah. So I did that first, I think. Yeah,
C minus b.
B minus c or c minus b. Which one do we do? I guess we could do c minus b. I think it was c minus b and c plus b, so it was like difference of square. I don't know. I forgot what happened in my complex. I don't know. Okay, whatever. Let's do c minus b.
Yeah.
So how do we factor out c minus b? It's like 1 from here.
Yeah.
Minus a squared. And then a... this is hard. Is it ab?
It's like c plus b on ab. So it's like a times c plus b on ab.
A...
Sorry, a times c plus b on b.
This is confusing as hell.
Yeah, maybe you can write it like without the bars.
I just wrote it with the bars, but now I've suddenly lost the ability to do it.
So b bar c minus bc bar. It's like c squared minus b squared on bc, right?
Ooh, what did I do? I think I did like...
Isn't it A and then like C plus B and then BC?
That's what it said.
I think I did like a b bar minus a c bar. Is that what I did?
Oh yeah, that works too. I think it's plus. Yeah, A plus.
Oh yeah.
Plus AC.
Is that right?
Yeah, that seems to work.
Okay.
It looks really weird though.
Yeah, because I'm not doing it very standardly.
A of a C, so it's A
Oh
B
my
bar
God.
plus A C bar.
What did I do? I don't even know.
I think that's correct.
Did I even do my algebra right? Like, I have no idea.
Correct.
Yeah. It just looks really funny.
Now I'm
It looks
paranoid.
like you just cancelled the C and the B and the sign.
I basically just I just canceled some weird stuff. I canceled the A's, so like if you multiply the A's.
Wait, that looks really crazy because it looks like you just take out the C minus B. that looks like one of those rookie errors, you know?
No, it's just facts. Trust me.
Wait, that feels like it's gotta be wrong then because if they're not the same,
This is weird.
if it were to be factorized like that,
This is so strange. What the?
but it is the same.
Okay, how did I do it? What the?
I mean, we keep going.
Like, what did I do? Did I do something wrong?
I think correct.
I swear it was wrong. Then I was like, how did I? I'm forgetting how I did it because like I have no idea. Let me see. How did I do it? Did I?
A bar.
I think. What did I factor out next?
Oh,
What did I factor
if you
out?
factor out A, like if you take A out, you get A bar plus B bar plus C bar minus A, which is like H bar minus A. Sauce.
I don't know if I did all my algebra correct up until this point. This is really sus. I don't know. Let me see. What did I do?
H bar minus. You want to show it's imaginary when you go to H, you know?
Did I just do A? What was it A? I guess it doesn't matter.
What shouldn't factor A plus B, right?
Yeah, we need to factor out A plus B plus 0 on this somehow. But
Factor out A plus B plus.
or at least like get a factor of A plus B plus C.
Well, if you factor an A,
And then the rest of it should be
if you take out A, then you get A bar plus B bar plus C bar.
A bar.
Minus A.
Wait,
What?
factor out A. Wait,
How-
that would be like 1 minus. Wait, A bar minus. Oh yeah, okay. Hold on.
So if you factor out A, you get H bar minus A.
C E.
What did I do? C. C bar.
Just at some point you could also even like set A equals 1.
What has A B bar C?
Just get a piece of paper.
Bro, this was like I don't even know.
Who else should be getting a piece of paper?
I just remember it was like something with it. Yeah, just synth it at this point.
No, I think this is no way you're not gonna solve this. It's just how messy it gets. But like
It does not get messy, definitely. It definitely does not get messy. But I don't know what I did. Because I... A plus A, B, B bar, C bar. C. What did I do?
I'm proceeding to figure out.
What did I do, dude? I don't know. Let me see. See what else? A bar, B minus A bar. Okay, that definitely.
What the? How's my diagram?
Did I do this right? It's like A.
Yes. Minus 1
Is this?
A squared
Did I mess up?
plus A B bar
Hold on.
plus A C bar.
A B bar C.
Factor A.
Wait, no, that's right. Okay.
Yeah. What? But A bar, right? It's A bar. It's A bar. Wait, how? What? Wait, what? Yeah. No. What?
What is going on?
Wait. A, C.
Oh wait. I think
C bar.
when you did
Wait, what?
R prime.
Wait, why did I add? Wait, no, I did add
Wait, when you did R prime,
yeah.
You have minus A.
You got A plus C minus AC R bar, right?
You have minus A here.
But the R bar didn't get barred. Like.
Oh wait, I'm dumb. Okay,
What happened?
I see. Okay, I see it. I see it. I see it. Okay, the R didn't get. Wait, no, I need to keep that one. I need to delete this one.
A bar. B
Yeah, it's A bar, B bar, C. That makes so much more sense. I blundered. Me when I can't do algebra. Okay, anyways, it's
It had to be a typo because the final
Yeah.
thing is not perpendicular.
yeah. It does not look right. Definitely does not look right. So this would become like B bar C squared or something. Yeah, that makes sense because it's homogeneous.
So it's A plus C plus B bar C squared
Yeah.
minus A B C bar.
And then it should be smooth from here because now we figured out blunder. I have blundered severely in algebra.
We figured out what the mistake was.
I figured out I did.
It was like there was the R bar wasn't barred.
Yeah, I didn't bar the R.
Like
And I didn't
R
bar the
prime
Q.
equals A plus C. Like the
Yeah,
R
I accidentally did it.
The R bar wasn't substituted for R bar. It was substituted for R.
Yes.
And this is C bar B's. Okay. Now this makes so much more sense.
No, it's C cubed minus.
C squared now.
Okay, that should be about right. And then what do I factor out? That's the question. I think I still factor out the same thing, unless I'm
C
mistaken.
minus B.
C. Hold on. I believe so. And then this becomes like C. What did... Okay, I know what I did for this. This was like the really sus. I removed the... This was the really sus part. And then this part, let me see. How does this work?
Plus. Yeah.
But yeah, I keep doing that. Never writing things. Oh, I see. I think it's a difference of squares. Yeah. Wait. Wait, was it a difference? Oh, it was a difference of cubes. Wait, what? I don't know. Wait, I forgot.
Yeah, like C cubed minus B cubed on BC.
Yeah, I think. It's like C cubed minus B cubed on BC. Which means like, if we divide out the C minus B, then we get like C squared on BC, which is like... BC. Is it 1 again? Yes. Is this right? B bar C times C. I mean B. That becomes C. Wait. What was it? Wait, is that right? Was that wrong? Am I bad? Am I having a skill issue? Oh wait, no. It does cancel. Just not very obviously. And then that becomes that, yep. And then finally you get B bar C squares minus C bar B. I believe this is it.
Let's see. Yes, that looks right. So it's a 2 plus.
Yeah. So this is
B bar, B, C bar, A, C bar, A, B bar. Indeed, this.
I am terminally ill at bad at algebra. How to not be bad at algebra. Not brain dead. Okay, so now what did I do? I did A, B, plus C. A, B, plus C. Wait, what? Was it B bar plus pause? If the algebra's wrong again, I swear to God. Cause like I swear it went way better when I did it. But now I'm being watched.
Seems right. Now you divide by H, is that what you're doing?
I think I can just
Or you're trying to factorize more stuff.
I feel like I can just power through. It's like, but I don't.
So, powering through.
Wait, A, B, bar, C bar. That becomes A, B bar and A, C bar.
Oh, wait. Yes, you can power through.
I see it. I think I see it. Yeah, I think I factored out like.
Yes, you're right.
Did I factor out B bar plus C bar?
Yeah, I think you can do that. And then
I think I factored out B bar plus C bar.
B bar plus C bar.
Wow.
That's
Okay, and then that gives me A plus B plus C, I think.
Yeah.
Wow. It's actually called factor of H.
That's actually, I did the same thing for everything else.
Wow.
Is it something?
I guess it's more obvious if you just get rid of the bar. Like, you get like, if you times it by BC, right? You get 2BC plus AB plus AC plus B squared plus C squared, right?
BC. Yeah.
And then it's obvious like
Yeah.
B squared plus C squared plus 2BC is a part of B plus C squared.
B plus. Okay, is this the correct?
Looks correct. The same thing.
And then, yeah, somehow this is imaginary. Is this obvious?
Oh.
Wait, that's kind of weird.
Okay, so obviously cancel the H. That's what he's thinking about. Cancel the H. You get C minus B times B bar plus C bar, right?
Is that even
The
right?
question is that's imaginary.
Is that imaginary? Or was there something else I did weird?
I mean, it's more obvious probably when if BC equals 1, that's pretty obvious.
Yeah. Oh, I think that's what I did. Oh, yeah, that's why it was so much easier for me when I did it, I think. Because I think I set B equals C bar like pretty early on when I reached like this point. And then it kind of just worked out.
So like C minus B and C plus B are perpendicular because they're like diagonals of a rhombus. Or you can just verify it's imaginary.
Yeah, and then they're perpendicular.
Then B bar, C bar.
Yeah, so like I guess it's like if C minus B and then they're perpendicular, then it's like reflecting this one and then adding the angle and it becomes 90. It's like if I bar this thing, it becomes like C bar minus B bar.
Yeah, it works out.
B plus C. And then
You given up, Andy?
what happened?
We're so close though.
What do I do to turn it into itself if I conjugate? I don't even know.
Yeah, no, you just get rid of the bars and then put the bars back in.
Oh, so it's like if I multiply it.
So like,
Oh yeah. So I basically take a BC factor out of this.
yeah.
So now this becomes B minus C, and then I put it in this factor.
Yeah.
And then
Yeah. So or you can say like both are equal to something from one BC.
and then plus is like commutative, so I don't need to change. And so now I have the negative of that.
Yeah, so is everyone able to show that C minus B times B bar plus C bar is imaginary? Yeah. When I asked everyone's staring at the screen. Why is that? You should all be able to do that independently, yeah? You know how to show C minus B times C bar plus B bar is imaginary?
What? Something about a rhombus.
Can you show that C is an algebra question? So C bar minus B times C bar plus B bar is imaginary. With B and C on the unison. Can you show that?
Bruh.
C minus B minus 1.
Lucas follow the bash.
C squared minus C squared.
C on B minus B on C.
Yeah, I guess this bash is kind of weird because I didn't really follow the tradition of like multiply all the conjugates out. I just kind of
the conjugates in there.
because the thing is like when I was doing it, I just saw the stuff and I was like, oh,
Interesting.
and then now I'm like dead.
Wait, so this is like your first official, I guess,
How do you show something imaginary?
like in
Isn't real part?
like completely unaided bash and present on live stage. That's like a milestone.
I missed this.
I don't know.
This is like this bash was done in the wild, like without any training wheels or anything.
I think this is a relatively like everything's relatively simple, so
I guess that's part of the
it's
skill
nice.
of bashing. There are maybe other paths that don't become simple. The crazy thing that H just cancels is crazy.
H. Yeah, I don't know. I think I was like the thing is for the two other points in my bash, I ended up using the same strategy of factoring out a plus b plus c,
Oh.
and it worked. It worked somehow. But the thing is, because I'm not like multiplying everything, all the conjugates out, it's way less obvious how to do it. So like a lot of the time I had to like try and coerce it to factor out by like adding random terms that somehow work. And so
maybe one of those is close to the general bash.
yeah.
I'm sure.
But I don't like I think I tried general proving class and then died.
It's good.
Yeah. I think when I first saw this problem,
I think it will.
my mind was like edging on something about like a fineness, because I was like, oh, everything's like if you move p at constant like at a constant rate, I guess these two also move at a constant rate. It's kind of like it's almost as if they can create parallel lines all the way through. But then I don't know. I got distracted. I got distracted on
Could you
something.
define a fineness as preserving ratios and
I don't know.
to preserve ratios, it should preserve parallel lines.
It's squared, it's real, right? Wait, are square numbers real? You know, like if C like
Are square numbers a real thing? Wait.
No, they're not real.
C squared is real, right?
No.
No, because like c squared is just the angle doubled along with.
Yeah, this bash is quite interesting. I think when I did it, I just immediately set B to C bar, and I was like, oh yeah, I'm done. And then now I'm just mega molding.
Oh, no wonder you filled out the application form as Dr. Sun's School of Complex Bash.
The one that we don't know.
I'll show you.
Okay, so
So should we try and synth this? Okay.
Yeah. What's B?
Wait, I thought we did just synth. Synthing is just simplifying the bash.
Synthing is just the bash, but like
Okay.
you don't say you're bashing. You just like
So,
say it in geometry
most of
language.
these are purely imaginary.
It's conjugate. Wait, it's negative of itself.
Yes. So what happens when you conjugate this?
It's very strange.
It's negative.
So okay, first let's look at this, right?
Yeah.
Was it C minus
Hmm.
right now? Right? So it's this. I believe it's B. It's like
What?
B minus
Oh.
Does anyone want to type this? Wait,
Oh,
Yeah,
I
right.
see. I see.
conjugate
did you
this.
pay for A-level
One
I
and
pizza?
think
one
I
and
understand, kind of.
C minus.
Oh, Andy, did you pay for A-level pizza? Oh, you didn't pay for pizza.
Yeah, okay, yeah.
Plus
Do you have any money?
minus C.
Let me see. How does this work?
So you can take that.
Wait, how does this work? I'm not too sure what I'm doing.
That's gaming, dude. I know the basics, but I'm not gonna. Nothing more. Nothing more. Oh, I remember I lost marks big time. The teacher didn't understand my method, which was basically proving something was purely imaginary.
Wait, it's 40 for both, right?
Oh,
I have $50.
yeah. I guess like proving something's purely imaginary is like
The $10
Wait, Andy,
It's like-
can I borrow?
it's like you can
Or
do it
what?
the school math way. You can also do it the complex
Okay.
bash TM way, and then no one knows what you're doing.
The conjugate way.
They're like, what is going
No,
on?
I just did
don't know.
because like because the
No,
magnitude of 5 plus C equals the magnitude of 5 minus C. So I'm like, okay, that's obviously imaginary. Because
I know, this is what Duke of Ed
Yeah.
Miss Ramsey died.
Oh.
What? Apparently she fell off a mountain bridge bivouac.
Alright, if you give me 50, that'll cover it.
Wait, what happened to Miss Ramsey? Apparently she like fell down like a mountain / cliff
What?
/ hill
No.
bivouac. Wait, Ryan, did you tell
I'm
us?
trying to figure out how to synth this, and so far I'm drawing a blank. I don't know how this
I
works.
marked the things and I sent it to pitch.
Apparently she fell down a mountain bridge
It's like
bivouac.
what? That's pizza equivalent.
Yeah,
No,
you still owe me an hour. I'll get that later.
Wait, are you?
Don't worry, there's plenty of work.
Are you joking? It's like joking, like
How is this? How is this simple?
Did you understand like all the notes?
Apparently. What bit was that? That was like last
Because
night.
I thought it was good, yeah.
Because
What the
I
heck?
I'll send it. I'll tell you them.
Sometimes it was too good.
No, she found out I think we were like.
But no frills, Mark.
I'm telling you, she found out I think. Why haven't I heard this yet?
Quality assurance.
No one bothered.
Alright, so
I'm not joking, bro.
There was parts where I was like, they keep the same worst case scenario. They're actually getting
Kidding, bro.
exploded.
that's how now you know how I feel. I swear I'm getting dumber when I'm up.
I'm not joking.
That's so true.
I'm not joking.
That's so true.
She's not
Is that the end of this question?
I think
That was pretty good. Like that's like question 3 of TST.
Apparently she lived back
That ain't
and
no
then
joke.
now she's just not at school. And I can't pay for my
Germany TST,
Oh, she didn't
but it's
die. She
bashable.
didn't die.
So now we go do it.
It wasn't quite bashful. Like it was like you made it bashful.
She's
I think
still alive though.
it was already bashable from the
she's
start
not dead.
because yeah, it was already bashable from the start because like you can do everything I just did with H with P, but it's just gonna be a lot more messy. And also, how do you define P? Like, there's like 2 ways that I can think of. Is like you can define P with lambda, or you can define P with like the condition, collinearity condition. I guess it's like it's kind of yeah. I don't know. But I guess the collinearity condition is not. It's not bad because you can define it by like. Oh, you can define it by like reflecting H here and then saying like it's like D or something. I'm saying like P reflects to itself on AD. I guess that's the condition. I don't know.
See,
I think when I was does it still exist?
when I was doing.
Does it still exist? Oh. This was the original attempt.
Should I put it on the video?
The original attempt before I gave up and Lucas mentioned MMP and I was like, what's MMP?
Let me put this on the video. Give me this.
Yo, we still have it.
I don't know if this is
World Heritage Site right here.
He says like,
World Heritage Site.
Hell yeah.
wait, is it? Can you see it?
I was attempting to bash it without MMP techniques at first.
See, can you see it on the screen? Is it on this screen? The laptop? Is it on the video?
Yeah. Yeah, it's on the video.
Look at the tree. And then just like
This is like really sad.
I'm like, okay, we need to speed this up.
Oh yeah, and there's also some Lagrange on here, man.
Lagrange.
Some random Lagrange.
Yeah, Alex.
And also some random SA6.
I think there's definitely room for labor hours or homework or whatever. Watch this video and then make the
I don't think anyone's ever gonna rub that.
make the write up the solution. Yeah.
Everyone else just laughs.
All right, that's it.